At the center of our galaxy, far beyond the clouds of stars you see in the night sky, there is a place where ordinary language almost fails. If you could peel away the dust and gas toward the constellation of Sagittarius, you would find a region where stars race around an invisible point, moving so fast that a single orbit can take only a few decades. All of that motion is driven by one object, a black hole with a mass of a few million suns packed into a space smaller than our solar system. The Milky Way is not special in this regard. When astronomers look at other large galaxies, they find the same pattern again and again. Spiral systems with graceful arms, giant elliptical swarms of stars, even some galaxies that look distorted and chaotic, all seem to hide a massive black hole in their core. In the biggest galaxies, the central object can contain billions of times the mass of the Sun. This raises a deceptively simple question. Why should the most extreme object in a galaxy almost always sit in the middle like a weight at the bottom of a cosmic bowl? If black holes can form from the death of massive stars scattered throughout a galaxy, why do the truly enormous ones end up buried in the heart instead of wandering somewhere in the outskirts? The more astronomers have measured these central monsters, the stranger the story has become. The mass of the black hole does not just grow at random. It seems to correlate with the mass of the central bulge of stars around it. Galaxies with heavier, denser cores tend to host heavier black holes, as if the galaxy and its central engine have been growing together, talking to each other through gravity and light for billions of years. So the puzzle is larger than simply asking why something heavy sinks to the middle. It is about how these central giants form, migrate, and then shape the entire system around them. Are they seeds from the very early universe that galaxies later built themselves around? Do smaller black holes slowly spiral inward over vast stretches of time, merging again and again until a single giant remains? Or is the connection deeper with the flows of gas that feed the black hole also sculpting the structure of the galaxy itself? To understand why black holes end up in the middle of galaxies, we have to rewind the story of structure formation in the universe back to an era before there were stars, before there were disks, and before any galaxy had a center at all. In the young universe, everything was simpler and more violent at the same time. Matter was spread unevenly, forming faint ripples in density left over from the first moments after the Big Bang. These ripples grew slowly under gravity, pulling gas into knots that would eventually become the first galaxies. But before any recognizable structure emerged, something essential happened. Matter began to fall toward the densest points of these ripples, creating natural centers long before anything resembling a star existed. Inside these growing clouds of primordial gas, the physics of collapse worked in a brutally straightforward way. Gas lost energy, cooled, and sank inward. As it did, the density at the center rose. This created a self-reinforcing cycle. Higher density meant stronger gravitational pull, which brought in even more gas, which increased density further. Over hundreds of millions of years, this process produced the first gravitational wells deep enough to turn collapsing gas directly into something extraordinary. The first massive black hole seeds. These objects were not born from dying stars the way smaller black holes are formed today. They emerged from entire clouds of gas, collapsing almost instantaneously under their own weight. Instead of breaking up into individual stars, the cloud contracted as a whole, skipping straight to a black hole that could weigh hundreds of thousands of suns. And crucially, this kind of collapse could only occur in the central region of a forming galaxy, where gas concentration was highest and gravitational pull strongest. It was not that black holes moved toward the center, they were born there. Once these massive seeds appeared, the conditions around them favored rapid growth. The very act of collapsing into a black hole left behind a turbulent environment rich in infalling gas. Every stream and filament of matter that flowed toward the newborn galaxy's central region brought material straight into the black hole's reach. The hole grew faster than any star, faster than any cluster, faster than nearly anything else in the early cosmos. This efficiency turned the black hole into a gravitational anchor. As gas spiraled inward, the entire galaxy took shape around that deepening well. Stars formed in dense pockets throughout the swirling cloud, but the core remained the region of highest pressure and highest inflow. Even as the galaxy evolved, building a disk forming spiral arms launching newborn stars outward, the center remained the most natural home for the black hole, because it was by construction the lowest point in the gravitational landscape. There is another ingredient that strengthened this central role: dark matter. Though invisible, dark matter makes up most of a galaxy's mass. It forms a large extended halo with its own center of gravity. This halo does not shine or react with light, but it controls where gas collects. Its densest point always lies at the center, and because the early black holes formed at that same position, they became embedded in the very heart of the galaxy's dark matter framework. In a sense, galaxies are not built around black holes. Both black holes and galaxies are built around the same gravitational center, the deepest pocket in the dark matter halo. The galaxy forms there, the black hole forms there, and their fates become intertwined from the beginning, long before the structure resembles the disks and spirals we see today. But forming at the center is only part of the story. For black holes to stay there over billions of years, even through collisions and mergers, something more has to hold them in place. And the universe provides exactly that. The deeper astronomers looked, the more one pattern kept repeating. Galaxies of every kind, spirals with sweeping arms, compact ellipticals glowing like cosmic embers, chaotic irregulars stitched together by ancient collisions, all seem to orbit a gravitational anchor far heavier than anything their stars alone could explain. That anchor was always the same kind of object, a supermassive black hole weighing millions to billions of times the mass of a star. And the remarkable thing was not only that these giants existed, but that they lived precisely at the centers as if the galaxy had arranged itself around them. This raised a question too important to ignore. Did the black hole form first pulling a galaxy around itself like iron filings around a magnet? Or did galaxies come first, with black holes growing only after enough matter funneled inward? The evidence refused to settle for one simple answer. Instead, galaxies behaved as if their cores and their central black holes grew together, locked in a feedback loop spanning billions of years. When young galaxies fed their black holes too quickly, jets of radiation blasted outward, heating surrounding gas and slowing star formation. When the feeding slowed, the gas cooled again, creating the next generation of stars. The heart and the body of the galaxy depended on each other, shaping one another in cycles older than Earth itself. But the reason black holes stay in the middle is even more striking. Gravity naturally drives heavier objects toward the center of a system, and nothing outweighs a supermassive black hole. Any slight drift, any minor displacement caused by a collision or merger is eventually damped out as countless stars pull the central giant back toward equilibrium. Even galaxy-scale disturbances cannot push it far for long. It is the ultimate anchor, a gravitational low point that everything else settles around. Yet there is one more surprise, something even stranger hidden in the math. The shape of galaxies, especially spirals, is partly the result of how angular momentum spreads through the entire system. Gas clouds falling inward do not simply plunge straight toward the black hole. They swirl, they flatten, they spin into vast disks. The black hole sits at the point where the swirling motion sums to zero, the only location where the chaotic dance of billions of stars becomes balanced. In a universe full of motion, the black hole occupies the one place where motion cancels itself out. And so the center of a galaxy becomes an inevitable home for a black hole, not by design but by physics. Wherever matter collapses on galactic scales, gravity funnels the heaviest concentrations toward the heart. Stellar corpses merge, gas clouds collapse, exotic objects form. Over cosmic time, the densest region becomes the birthplace of something so heavy and so compact that nothing else can rival it. The galaxy does not simply host a black hole. It grows around one, When galaxies collide, and they do so far more often than intuition suggests, their central black holes are drawn into an even deeper gravitational drama. Two entire star systems can pass through each other like ghosts, their stars barely touching, yet their central black holes feel each other instantly. As the galaxies merge, the dense cores sink inward, carried by the drag of countless gravitational interactions. Eventually, the two black holes fall toward the shared center of the newly formed galaxy, spiraling closer as they shed energy into the surrounding sea of stars. Even when the merger is violent, even when the newborn galaxy is twisted into tidal arcs and chaotic streams, the black holes never wander far from the gravitational minimum. They oscillate briefly like heavy weights dropped into a bowl, but every wobble shrinks with time. The core of the galaxy, a region packed with stars, gas and dark matter, absorbs their motion and pulls them back toward the center. If the two giants combine, they release a burst of gravitational waves that ripples through space-time. That recoil can nudge the merged black hole off-center, but not for long. The galaxy's mass, extending millions of light-years around it, slowly reins it in again. The universe always restores the balance. This central migration has another consequence. It ensures that galaxies almost never end up without a black hole. Even if a galaxy started with several massive seeds, mergers gradually funnel them inward until only one remains at the core. Small holes fall toward big ones. Wandering remnants left from earlier epochs spiral inward over billions of years. A galaxy's center becomes a gravitational clearinghouse, sweeping up anything compact, heavy, or ancient enough to drift through its crowded neighborhoods. Over time, the central region becomes the only place where the largest black hole can survive without being torn apart or dragged elsewhere. But the relationship does not end there, because the black hole does not merely sit at the center. It actively influences the structure around it. When material falls inward, it heats up and emits intense radiation. This radiation in turn pushes on surrounding gas, preventing it from collapsing too quickly into stars. Without this regulation, galaxies would burn through their star-forming material in a rapid burst and fade long before the present day. The central black hole behaves like a cosmic thermostat, limiting runaway growth and shaping the rhythm of stellar birth. In some galaxies, this regulation becomes extreme. Their black holes flare as brilliant quasars, shining brighter than entire clusters of galaxies. For a brief moment in cosmic history, the center becomes the dominant source of energy, blasting jets thousands of light-years long. Yet even during these explosive phases, the black hole remains bound to the middle. The forces it unleashes radiate outward, not inward, because the center is already the lowest point in the gravitational landscape. No matter how violently it feeds, it cannot escape its own cosmic anchor. As the galaxy ages, the activity quiets. The black hole settles into a dormant state, swallowing only the occasional star or cloud that wanders too close. The surrounding stars continue their orbits, tracing graceful paths around a point they cannot see, but whose presence they constantly feel. The galaxy becomes a stable system maintained not just by gravity, but by the ancient imprint of the black hole's formation. And so the answer becomes clear. Black holes sit at the centers of galaxies because the centers are where gravity, history, and cosmic structure converge. They form there, they grow there, and the very shape of the galaxy keeps them there. Yet the story is still not complete, because the connection between a galaxy and its central black hole runs deeper than simple gravitational convenience. Astronomers have discovered a remarkable proportionality. The mass of the central black hole tightly correlates with the mass of the galaxy's bulge, the dense star-filled region surrounding the core. This is not a loose trend. It is a relationship so precise that measuring the bulge can almost predict the black hole's mass and vice versa. Something in the early universe forged this link, binding two very different structures into a shared evolutionary path. This correlation suggests a long, slow conversation between the galaxy and its core. When gas floods toward the center and feeds the black hole, it produces outflows powerful enough to stir the entire inner region. These outflows prevent too many stars from forming too quickly, maintaining a balance that keeps the bulge from collapsing into chaos. At the same time, the bulge provides a deep reservoir of matter that occasionally drifts inward, allowing the black hole to grow in measured bursts. It is a feedback system millions of light-years wide, driven by gravity energy and the flow of interstellar gas. Over billions of years, this quiet exchange builds galaxies that reflect the nature of their cores. A galaxy with a massive bulge tends to host a massive black hole. A galaxy with a lighter bulge tends to have a smaller one. Even galaxies that appear irregular or distorted often hide a core whose mass fits the same scaling law. It is as if every galaxy carries an internal blueprint etched into space-time long before its stars formed. But not all galaxies are large enough to create such giants. The smallest galaxies, faint dwarfs drifting through the outskirts of galaxy clusters, often lack the dense centers needed to form or maintain a massive black hole. Their gravitational wells are shallow, gas flows unevenly, mergers shake their structure. Many may contain black holes too small to detect with current instruments, while others may genuinely have none. But rather than being exceptions to the rule, these galaxies highlight it. Without a deep central potential, well, a galaxy cannot reliably form or anchor a massive black hole. The absence of a core giant simply reflects the absence of the conditions required to create one. Meanwhile, in larger galaxies like the Milky Way, the central black hole is stable and permanent. Even if it rarely feeds today, its gravity shapes the motion of everything within a few light years. Stars whip around the center at astonishing speeds, tracing invisible ellipses around a point of darkness. Their orbits provide some of the strongest evidence that the black hole is truly there, quietly anchoring our galaxy as it drifts through the cosmic web. As galaxies continue their lives, merging, shifting, absorbing smaller neighbors, their central black holes act like long-lived fossils of cosmic history. Each one remembers every collision it has endured. Each one carries the mass of everything it has consumed. And each one stays locked in place, held by the combined weight of billions of stars and trillions of tons of gas resting at the natural minimum of the gravitational world around it. Over time, this central anchor becomes more than just a massive object. It becomes a stabilizing influence on the galaxy's internal structure. When stars orbit the center, their combined motion creates a gravitational symmetry that keeps the disk from warping too violently. The presence of a compact heavy object helps maintain the orientation of orbits over billions of years, preventing the inner regions from becoming chaotic. It is not that the black hole actively organizes the galaxy, rather its mass provides the balance point around which order naturally arises. This balance is reflected in the remarkable calmness of our own galactic core today. Sagittarius A, the Milky Way's central black hole, is comparatively quiet. It swallows very little matter and shines faintly compared to the brilliant quasars found in distant galaxies. But even in its dormancy, it remains the dynamic heart of the system. The orbits of nearby stars reveal its influence with exquisite clarity, mapping a gravitational well so deep that only a supermassive black hole could create it. And although the black hole appears still, the region around it is shaped by countless invisible interactions. Gas clouds drift through the central light years, stretching into filaments as tidal forces tear them apart. Occasionally, one of these clouds strays too close, feeding the black hole with a brief flare of radiation. The core becomes a laboratory where gravity, magnetic fields, and turbulence intertwine in a way found nowhere else in the galaxy. These moments of activity remind astronomers that the central black hole is not a dead relic, but a living part of the cosmic environment. Even in galaxies with intense star formation, the black hole maintains its place. Supernova explosions, stellar winds, and inflowing gas all compete for dominance, yet the central massive object remains unmoved. The galaxy behaves like a storm whose eye stays anchored in place. Everything around it swirls, burns, collides, and evolves, but the center remains the center, not by chance, but by the uncompromising logic of gravity. As galaxies age, their disks thicken, their star formation slows, and their gas reserves fade. But the central black hole does not fade with them. It persists an ancient core around which everything else rearranges. Long after the outer arms dissolve and the bright spiral patterns soften into diffuse halos the central black hole endures, it becomes a memory of what the galaxy once was, holding a record encoded in mass rather than light. Even more astonishing is how this central mass influences the trajectories of objects far beyond its immediate neighborhood. Stars tens of thousands of light years away, stars that will never come close to the black hole, still respond to the overall gravitational geometry that the central mass helps define. It is a subtle effect drowned out by the combined pull of billions of other stars and the dark matter halo. Yet the black hole's presence is woven into the overall balance of motions. Remove it, and the galaxy would not collapse or tear apart, but the symmetries that have held for billions of years would be altered. It is a reminder that even though the black hole is tiny compared to the whole galaxy, it occupies a position that maximizes its influence. This influence reaches a climax during periods of heavy accretion. When streams of cold gas fall inward from the outer disk, the black hole awakens. A swirling accretion disk forms, heating to extreme temperatures. Magnetic fields twist into colossal structures. In some cases, narrow jets erupt from the poles, shooting material far into intergalactic space. These jets can extend for hundreds of thousands of light years longer than the galaxy that launched them. And yet all of this activity remains centered on a point smaller than our solar system, an engine of unimaginable power anchored in the quiet core. The impact of these outbursts ripples throughout the galaxy. Gas clouds that might have formed new stars are pushed outward, slowed or heated beyond the point of collapse. Cavities are carved into the interstellar medium. Shockwaves propagate through the disk. Over millions of years, these processes regulate how the galaxy uses its fuel, preventing runaway star formation. Without this balancing act, galaxies could consume themselves too quickly, burning bright for a moment but fading long before their time. The black hole's position at the center ensures that this regulation affects the heart of the galaxy, first creating conditions for long-term stability. Even after these storms subsided, the imprint remained. Astronomers examining galaxies across cosmic time find signatures of ancient outflows fossilized in their gas distributions. Rings, bubbles, and asymmetries often trace back to periods when the central black hole was far more active than it is today. They are marks of an era when energy erupted from the core and shaped everything around it. Quiet now, but still visible in the patterns of light and shadow. And through all of this, the black hole remains anchored. Even if a galaxy is warped by tidal forces from a passing neighbor, even if star clusters rain inward or streams of dark matter shift slightly, the black hole does not drift. Its position at the bottom of the gravitational well ensures that it is the most stable location in the entire system. If the galaxy were a landscape, the black hole would be the deepest valley, the lowest point where everything else eventually rolls. What is remarkable is that this central position is not the result of a single mechanism, but the convergence of many. The way matter collapses the role of dark matter, the flow of gas, the feedback from accretion, the damping of motion through billions of gravitational encounters, and the stabilizing geometry of a rotating disk. No single factor places a black hole in the center. The center is simply the one place where all factors meet. This convergence becomes even clearer when astronomers simulate galaxy formation on supercomputers. When they start with the conditions of the early universe, slight density variations, cooling gas, and an evolving dark matter scaffold galaxies emerge naturally. Their centers grow denser faster than their outskirts. Gas flows inward along filaments that stretch across millions of light years, funneling material directly into the core. In every realistic simulation, when the density at the center crosses a critical threshold, a massive black hole forms, and once it forms, its growth is inevitable. These simulations reveal something profound. Even when researchers remove certain ingredients, cooling processes, star formation feedback from radiation, the center still forms first. The gravitational equations alone dictate that the densest region collapses faster than everything else. In other words, the universe does not have to prefer the center. The center is simply where the laws of physics converge to produce extremes. But the presence of a central black hole does more than respond to this collapse. It reinforces it. As the black hole grows, it deepens the potential well-pulling gas even more efficiently into the inner few light years. This accelerates star formation near the core and increases the density contrast between the center and the outer disk. Even when the black hole later quiets down, this structural imprint remains like the memory of an earlier gravitational storm, and as the galaxy continues to evolve, this imprint guides its long-term behavior. Bars form in spiral galaxies funneling gas inward. Collisions reshape stellar orbits, but always funnel mass toward the lowest gravitational point. Even the slow migration of stars through the disk, driven by billions of tiny gravitational nudges, contributes to a gentle inward drift of mass over cosmic timescales. Every one of these processes moves material toward the core, not away. This is why, even in galaxies where the central black hole appears too small to dominate the overall gravity, it still sits exactly where the galaxy's structure naturally settles. The black hole is not an intruder, not an afterthought, not a wanderer. It is a byproduct of the same forces that shape the entire system. It grows in step with the galaxy because both the star-filled disk and the central hole are responding to the same underlying physics. And so when astronomers map the motions of stars' gas clouds and even the faint glow of dark matter within galaxies, they find a pattern as consistent as the orbits of planets around a star. Everything ultimately references the core. Everything responds directly or indirectly to the gravitational valley carved out during the galaxy's earliest moments. The center is not simply a location, it is a consequence of the cosmic landscape. In the largest galaxies, this gravitational landscape becomes especially dramatic. Their central black holes can reach masses of several billion suns, forming objects so compact that their event horizons could swallow our entire solar system. Yet despite their unimaginable density, they represent only a tiny fraction of the galaxy's total mass. A typical massive galaxy may weigh hundreds of billions of solar masses, meaning the black hole accounts for far less than 1% of the whole, and still it occupies the one position that matters most. Its mass is not what grants it dominance, its location is. This distinction is crucial. The black hole's gravitational pull is overwhelming only within a small radius. Beyond that inner region, the combined gravity of the galaxy's stars and dark matter halo far outweighs the black hole's influence. Most stars in the galaxy would hardly notice if the black hole doubled or even tripled in mass. What they would notice immediately and profoundly is if the central anchor were removed or displaced from the core, the galaxy's symmetry would falter. Stellar orbits would shift. The structure of the disk could warp over billions of years. This center exists not because the black hole demands it, but because the galaxy requires it. This requirement becomes even clearer when black holes interact with dense star clusters. When a cluster passes close to the core, it can be torn apart by tidal forces, leaving streams of stars spiraling inward. Over time, these streams mix and settle, reinforcing the central mass distribution, even if a black hole were slightly displaced. Events like these would drag it back into alignment with the galaxy's deepest gravitational point. The entire system behaves like a self-correcting mechanism, constantly erasing deviations and restoring its internal balance. On rare occasions, gravitational waves from a black hole merger can impart a recoil strong enough to push the merged black hole several light years away from the center. Astronomers have even found hints of such recoiling giants, black holes drifting within their host galaxies like heavy ships in a cosmic harbor. But these events never break the underlying rule. The recoil slows, the galaxy's mass reclaims its center, and the black hole sinks back into place like a stone settling at the bottom of a deep pond. Through all of this, one principle repeats: The physical center of a galaxy is the most stable destination for anything massive and long-lived. No other region offers the same gravitational equilibrium. No other region collects as much material over time. No other region provides the conditions necessary for supermassive black holes to form and endure. Even when chaos reigns, when galaxies collide, when starbursts ignite, when jets carve through intergalactic space, the center remains an anchor point. The universe continually reinforces. As a result, the central black hole becomes a kind of historical record. Its mass reflects every era of the galaxy's growth, from the early collapse of primordial gas to the late-time trickle of wandering stars. Its spin remembers the directions of ancient mergers. Its quiet or violent phases trace the flows of matter across cosmic epochs. In this way, the central position is not only a matter of gravity, it is a matter of memory. This idea of black holes as archival objects becomes especially compelling when astronomers examine galaxies across cosmic time. In the most distant galaxy systems whose light began travelling toward us, when the universe was only a fraction of its current age, the central black holes are often astonishingly massive. Some weigh 1 billion suns when the universe was less than 1 billion years old. That growth is too rapid to explain by the deaths of massive stars alone. It requires an early and sustained supply of gas funneled into the core of proto-galaxies before they had even settled into familiar shapes. These ancient quasars reveal a truth that reshapes our understanding of structure formation. The center of a galaxy becomes extreme not because the outskirts are unimportant, but because everything that defines the galaxy gas flows. Dark matter, potential. Cooling rates, collapse times naturally converges toward the core. In the early universe, when matter was dense and temperatures were high, this convergence was overwhelming. Once a seed black hole formed at the center, it became the primary beneficiary of every subsequent inflow of gas. Growth was not random. It was guided by the architecture of the universe itself. As galaxies aged and matured, their centers stabilized. Bulges formed from repeated mergers of smaller fragments. Disks settled into broad rotating structures shaped by the conservation of angular momentum. Bars developed channeling material inward like rivers feeding a lake. Everywhere in this evolving system, gravitational forces work tirelessly toward equilibrium. An equilibrium was always found at the center. Dark matter too played its silent role. Its halo shaped the deepest contours of the gravitational well. Although dark matter does not collapse into thin disks like visible gas does, its densest point lies exactly where the earliest black hole seeds formed. Over time, the baryonic matter-gas star's dust rearranged itself around the halo's core, not because the black hole demanded it, but because the dark matter sculpted the stage long before the black hole arrived. The galaxy was destined to have a center, and the black hole was destined to occupy it. Even the chaotic processes that might seem capable of dislodging a black hole end up reinforcing this destiny. When galaxies merge, their black holes are dragged along paths that ultimately lead them to the deepest point of the combined system. When massive star clusters fall inward, their gravitational wake dampens any off-center motion. When clouds of gas stream toward the core, their angular momentum dissipates in shocks and turbulence, allowing some of the material to plunge straight toward the black hole. Every mechanism that redistributes energy and motion in a galaxy, no matter how messy, tends to drive matter inward. This is why the question, why are black holes in the middle of galaxies, is both simple and profound. They are there because everything in the universe prefers the center. Gas prefers it. Stars prefer it. Dark matter prefers it. Gravity enforces it. History records it. And black holes, being the densest objects of all, simply sink to the place that all structures eventually point toward. Their central position is not imposed. It is inevitable. Over billions of years, this inevitability becomes the defining signature of galactic structure. Even as stars migrate, even as spiral arms twist and dissolve, even as dust cools and gas thins out, the gravitational center remains fixed. It is the reference point for every orbit, the location where velocities balance the place where the galaxy's deepest potential well resides. And because supermassive black holes formed in these wells from the earliest epochs, they inherit a position of permanent residency. The most compelling evidence for this comes from observing stars in galactic centers themselves. In the Milky Way, the orbits of stars near Sagittarius A draw perfect loops and ellipses around a point of darkness. These orbits are measured with astonishing precision tracing paths that reveal the mass hidden at the core. No alternative explanation, not clusters of dark stars, not clouds of compact objects, can account for their speeds or their tight curves. Only a supermassive black hole fits the data. Its presence is undeniable, and its location is exactly where theory predicts the gravitational center should be. When astronomers look beyond our galaxy, the pattern repeats. Giant ellipticals contain massive black holes proportionate to their dense stellar cores. Luminous quasars shine from centers so bright that entire galaxies are washed out by their glare, yet their light always comes from the very heart of their host systems. Even the faint signatures of low-mass black holes in smaller galaxies point to a common theme. Centrality is not coincidence. It is the natural consequence of billions of years of gravitational evolution. What makes this insight even more elegant is how little fine-tuning the universe requires. There is no special instruction embedded in the laws of physics telling black holes where to sit. No cosmic architect assigns them roles or locations. The distribution of matter, the collapse of early structures, the cooling of gas, the shape of dark matter, halos, and the internal dynamics of stars all create a gravitational landscape with a single, unavoidable low point. And anything sufficiently heavy, especially an object as dense as a supermassive black hole, will always find its way to that point. In this sense, the question transforms from why are black holes in the middle to something even more revealing: how could they be anywhere else? Every process that builds galaxies funnels mass toward the core. Every disturbance that might dislodge a black hole eventually fades, pulled back by the combined weight of billions of stars. Every inflow of gas, every merger, every internal instability reinforces the central gravitational well. The black hole is not placed at the center. It is grown there, held there, and preserved there by the architecture of the cosmos. And perhaps the most striking realization is that the black hole's central position is not just a structural fact, but a narrative one. It tells the story of how galaxies assembled from the first cooling gas clouds. It records the mergers that built their bulges. It preserves the memory of ancient quasars that once lit up the young universe. The black hole stands in the middle, not because it dominates the galaxy, but because it reflects its long and intricate history, a quiet monument to the forces that sculpted everything around it. In the end, the black hole at the center of a galaxy is far more than a point of darkness. It is the oldest surviving witness to that galaxy's birth. It formed when the universe was young, when matter was raw, when gravity sculpted the first structures out of chaos. It grew as gas spiraled inward, as stars ignited, as mergers stitched fragments into something larger and more luminous. It endured every collision, every tidal shock, every storm of radiation. And through all of it, it remained where it began, anchored in the deepest part of the gravitational well. Its central position is not a coincidence and not a mystery the universe hides from us. It is the natural outcome of billions of years of motion collapse and equilibrium. The galaxy built itself around this core because all of its matter obeyed the same fundamental laws. The black hole is not the master of the system nor its servant. It is the memory of its earlier structure preserved in a single compact form. When we look toward the center of the Milky Way, we are not just seeing a distant region of space. We are looking at a remnant of the universe's beginning, a relic older than any star, older than the spiral arms, older than the disk itself. A silent gravitational archive storing the history of everything that has ever fallen into it. And perhaps that is the most profound truth hidden inside every galaxy. The center is not simply a place where gravity is strongest. It is where the story began. Black holes did not move to the middle. They were born there, grew there, and remain there because the architecture of the cosmos leaves them no other home. Every galaxy carries such a heart, a point where its past, present, and future meet, a place where light bends, where time stretches, and where the oldest chapters of cosmic history are still being written, one falling star at a time. 50 million light-years from Earth, in the heart of a giant galaxy, there is a place where light bends into a perfect ring, and space folds so steeply that nothing can escape. In 2019, humanity saw that place for the first time. It appeared as a glowing circle of distorted fire wrapped around a hollow center, an image so strange, so precise, that it seemed less like a photograph and more like a message carved into space-time itself. That shadow belongs to the black hole at the center of M87, an object so massive it could swallow our entire solar system. It sits at the core of the galaxy Messier 87, a titanic elliptical cluster of stars whose mass stretches far beyond anything in the Milky Way. For decades, astronomers suspected that something enormous was hiding in that central region, but suspicion is not the same as sight. Only when telescopes across Earth combine their signals into one planet-sized eye did the black hole finally reveal its shape. The moment the image came into focus, a century of predictions crystallized in a single frame. The dark interior matched the size Einstein's equations demanded. The halo of plasma glowed exactly where gravity and relativistic motion said it should. For the first time, we were not imagining a black hole. We were looking at one, and yet the picture was only the beginning. To understand M87, to understand why this black hole looks the way it does, how it formed, and what it tells us about the universe, we must step deeper into the story of the galaxy that surrounds it, the disk of scorching plasma that feeds it, and the jet that erupts from its poles like a cosmic lighthouse visible across intergalactic space. M87 is not a typical galaxy. It has no graceful spiral arms, no delicate lanes of dust curling across a thin disk. Instead, it rises in the Virgo cluster like a cosmic citadel, a vast rounded swarm of ancient stars bound together by gravity on a scale that dwarfs the Milky Way. While our galaxy contains a few 100 billion stars, M87 holds several trillion. Its light stretches 50,000 light-years from the core in every direction, forming a smooth, diffuse glow that reveals a structure shaped not by rotation, but by violent history. Elliptical galaxies like M87 are built through collisions and mergers. Over billions of years, smaller galaxies fell inward, combined and dissolved into its expanding halo. Each merger stirred the stars, erasing patterns and smoothing out rotation, until the galaxy became a nearly spherical reservoir of mass. This long sequence of cosmic traumas created a place where the center is unimaginably dense, a region where gravity has been reinforced again and again by every system that M87 consumed. At the heart of this luminous cloud lies a core so bright that early astronomers suspected it hid something extraordinary. The stars there move at tremendous speeds, swirling around a point they cannot see. The motions hinted at mass far beyond what starlight alone could explain, as if a giant were sitting in the center pulling everything inward. By the late 20th century, the evidence was clear. Only a supermassive black hole could account for such extreme dynamics. And so the search began. Radio telescopes revealed powerful emissions from the core, along with a jet so enormous that it extended thousands of light-years into intergalactic space. The scale of this jet was a clue. Only an object of staggering mass and energy could launch such a structure and keep it stable for millions of years. Everything pointed to the same conclusion. The black hole in M87 was one of the largest in the known universe. Understanding the galaxy that surrounds it is essential because M87 is not just a backdrop. It is the environment that allowed this colossal black hole to form and grow. Its density, its history of mergers, and its vast reservoir of hot gas all contributed to the creation of a gravitational engine unlike anything in our region of space. To understand the black hole, we must understand its host, the giant that made it possible. The black hole in the center of M87 is a giant beyond ordinary comprehension. Estimates place its mass at roughly 6.5 billion times that of the Sun, a number so large that the mind cannot hold it all at once. To understand it, we must translate it into scale. If you replace the Sun with this black hole, its event horizon would reach far past the orbit of Pluto. The entire solar system, along with every planet we know, would fit comfortably inside its dark interior with room to spare. Yet despite its size, the black hole's edge is deceptively small on cosmic terms. Space near the event horizon is compressed by gravity so intensely that it behaves like a curved wall, bending light into loops and spirals. This bending produces the glowing ring we see in the famous image, not a surface, but the paths of photons trapped in orbits just outside the point of no return. The ring itself spans a region comparable to the width of our solar system, but the forces shaping it are so extreme that the slightest change in angle determines whether a beam of light escapes or vanishes forever. The mass of M87's black hole also determines how violently the surrounding matter behaves. Gas falling toward it does not drop straight in. It forms a disk of plasma orbiting at nearly the speed of light. Temperatures rise to trillions of degrees. Magnetic fields twist into tight spirals. These conditions create a furnace so intense that even before matter crosses the event horizon, it emits radiation powerful enough to be detected millions of light years away. The glow we see is not a gentle beacon. It is the light of matter being torn apart by gravity pushed to its limit. This scale also explains why M87 was chosen as the first target for the Event Horizon Telescope. A black hole this massive has a shadow large enough to be imaged from Earth, even across 50 million light-years. Smaller black holes, including the one in the Milky Way, have event horizons too tiny and too dynamic to resolve easily. M87, by contrast, is enormous, steady and bright in the radio wavelengths needed to map the edge of space-time itself, when astronomers calculate the dimensions of 87's shadow. The result matches the predictions of general relativity with remarkable precision. The diameter of the dark region corresponds exactly to what Einstein's theory demands for a black hole of its mass. It is a rare moment in science when the abstract curves of an equation materialize into a visible structure floating in the cosmos. A black hole may be defined by darkness, but in M87 the most striking feature is a beam of light. From the galaxy's core, a jet of plasma erupts outward at nearly the speed of light, extending thousands of light-years into intergalactic space. It burns like a cosmic torch, visible even in modest telescopes, cutting across the faint halo of stars with a precision that seems almost engineered. No other structure in M87 is as iconic. It is the galaxy's signature, a signpost pointing directly to the power of the black hole that anchors it. Jets of this scale do not form from the black hole itself because the black hole releases no light. Instead, they emerge from the sprawling disk of material orbiting around it. In the inner regions of this disk, magnetic fields wrap around the spinning black hole like threads round a spindle. As the plasma spirals inward, these magnetic fields tighten, twisting into powerful bundles that guide charged particles along narrow paths. The result is a focused stream of energy launched from the poles, sculpted by magnetism and driven by rotational power, extracted from the very fabric of space-time. What makes M87's jet extraordinary is its stability. This colossal beam has persisted for millions of years, maintaining its direction with remarkable precision. Even across epochs of galactic evolution, collisions, inflows and turbulence, the jet appears almost unchanged. The consistency suggests that the black hole spins rapidly, locking the jet to a stable axis. This spin, combined with the sheer mass of M87's core, creates conditions that amplify the jet to scales seen in only a small fraction of galaxies. The jet also reveals details of the environment around the black hole. As the beam travels outward, it interacts with surrounding gas, heating it, and forcing it into glowing knots that trace the jet's path. These structures give astronomers a way to measure the speed, density, and energy flow of material leaving the core. By analysing the light from these knots, scientists can probe processes happening within a region only a few times larger than the event horizon, a feat otherwise impossible given the black hole's distance from Earth. Despite its brightness, the jet carries only a small fraction of the matter that falls toward the black hole. Most of the gas spirals inward and disappears, but the jet represents something else, a window into the physics of strong gravity and intense magnetic fields. In studying it, astronomers are not just observing a stream of particles, they are watching a machine powered by the rotation of space-time itself. The glow surrounding the center of M87 does not come from the black hole itself. No light escapes from the region inside the event horizon. Instead, everything we see in the famous image is produced by the maelstrom of plasma spiraling around it, the accretion disk. This disk is a turbulent radiant structure where matter reaches temperatures so extreme that electrons and ions break apart, forming a fluid of charged particles racing close to the speed of light. In this environment, gravity, magnetism, and motion collide in a way that exists nowhere else in the galaxy. As the plasma swirls inward, it accelerates until its velocity becomes a significant fraction of light speed. Motion at these extremes produces a relativistic effect that sculpts the image. Light emitted from the side of the disk moving toward us becomes brighter, boosted by the motion of the particles. Light from the side moving away from us becomes dimmer. This brightness contrast creates the asymmetry visible in the glowing ring, a subtle tilt that reveals the direction of the disk's rotation and the orientation of the black hole's spin. Closer to the event horizon, gravity becomes overwhelming. Space curves so sharply that photons, particles of light, can be trapped in unstable orbits. Some circle the black hole one or more times before escaping. Others fall inward, never to return. The boundary between these fates forms a thin, bright ring called the photon ring. It is not a physical surface, but a structure of probability carved by gravity itself. Its presence outlines the shadow, the dark region where no light emerges. This shadow is larger than the event horizon because gravity bends light around the black hole. Any phaon passing too close is redirected, warped into arcs that contribute to the glowing ring we see. The shadow, therefore, is the silhouette of the event horizon magnified by space-time. Its shape provides a direct fingerprint of the black hole's mass and confirms the predictions of general relativity and the strongest gravitational fields nature can produce. The accretion disk's behavior also reveals the environment feeding the black hole. Turbulence within the disk, powered by magnetic instabilities, transfers angular momentum outward. This allows gas to fall inward in a slow but unstoppable spiral. Every particle that crosses the event horizon releases a flash of radiation just before disappearing, adding to the chaotic brilliance of the disk. The heat, the motion, and the magnetic fields combine to create an enormous laboratory, one we can study only through the shape and brightness of the ring at its edge. The image from M87 is not a picture of the black hole itself, but of its influence. It is the visible imprint of gravity on light, a rare glimpse of the boundary between our universe and a region where space and time collapse inward. And because the physics shaping this image is so extreme, even small deviations from Einstein's equations would distort the shadow. The fact that the observed ring matches the predictions is one of the most powerful confirmations of general relativity ever obtained. Seeing the region around a black hole requires something more powerful than any single telescope on Earth. The details of M87's shadow are so fine that even the largest observatory would blur them into nothing. To resolve a structure the size of our solar system from 50 million light-years away, astronomers needed an instrument the size of a planet, and so they built one not by constructing a new telescope, but by connecting existing ones scattered across the globe. This array became the Event Horizon Telescope, a worldwide network of radio observatories working together as a single eye. From the deserts of Chile to the peaks of Hawaii, from Mexico to Spain, from Arizona to the South Pole, each dish recorded faint signals arriving from M87 at the exact same time. These signals were stored with extreme precision, synchronized by atomic clocks accurate to billionths of a second. Later supercomputers would combine the data using a technique called very long baseline interferometry to simulate a virtual telescope as wide as Earth itself. The challenge was immense. Weather at any site could disrupt observations. The atmosphere could distort incoming light. The rotation of Earth meant the array's geometry changed minute by minute. To overcome this, the team observed M87 repeatedly collecting petabytes of data so large that it could not be transmitted digitally. Instead, the hard drives themselves were flown to processing centers in the United States and Germany, where the signals were aligned and merged. What emerged from this effort was not a simple photograph. It was a reconstruction built from thousands of tiny measurements, each representing a fragment of the wavefront arriving from M87's core. These fragments were stitched together by algorithms designed to fill in the missing pieces while remaining faithful to the laws of physics. The process was so intricate that the team developed multiple independent pipelines to ensure no hidden bias shaped the result. In the end, every method pointed to the same image, a bright crescent wrapping around a dark circular shadow. This was the unmistakable imprint of a black hole. The brightness asymmetry revealed the direction of the accretion disk. The diameter of the shadow matched the mass predicted from stellar motion. The dark center lined up exactly with general relativity's forecast for a region where nothing, not even light, can return. The achievement was unprecedented. For the first time, humanity had built an instrument capable of probing the edge of space-time itself. The Event Horizon Telescope did not simply show us M87's black hole. It demonstrated that we could, with enough precision and enough imagination, turn an entire planet into a window onto the deepest gravitational well ever observed. When the final image was unveiled on April 10, 2019, the world paused. On screens across the planet appeared a ring of fire wrapped around a circle of darkness, a shape that had existed only in equations, simulations, and imagination. For decades, black holes were symbols of abstraction objects defined by mathematics rather than sight. But now the boundary between theory and observation had blurred. The shadow of a black hole had become visible. The image carried weight far beyond its simple form. The dark core matched the predicted size of a black hole with billions of solar masses. The bright arc aligned with models of plasma swirling at relativistic speeds. The symmetry and curvature of the ring affirmed that space-time bends light exactly as Einstein's theory demands. Every feature in the picture, from the thickness of the ring to its lopsided glow, reinforced a century of physics. It was proof that general relativity, a theory conceived long before humanity understood galaxies or cosmic jets, still describes the universe with extraordinary accuracy. For astronomers, the moment was transformative. The silhouette of M87's black hole confirmed that the event horizon is a real boundary, not just a mathematical convenience. It validated decades of work on accretion disks, magnetohydrodynamics, and gravitational lensing. It offered new tool for measuring black hole spin mass and geometry, and it paved the way for future observations that may one day reveal the turbulent dance of plasma orbiting the shadow in real time. But the impact stretched beyond science. The image became a symbol of collective human effort. Hundreds of researchers, dozens of institutions, multiple continents, and years of coordination working toward a single goal. It demonstrated the power of collaboration at a scale rarely seen in astronomy. Each pixel in the image represented not only the light from a distant galaxy, but the combined expertise of people who refused to accept that a black hole was forever beyond sight. The reaction from the public was immediate. The picture spread across newspapers, television, and social media. For many, it was the first time the concept of a black hole felt tangible. People described the image as unsettling. beautiful or profound, but nearly everyone recognized its significance. This was a direct glimpse into the most extreme environment in the universe. And yet the image was only a starting point. Its success raised new questions about the nature of black hole spin, the stability of the jet, and the deeper physics hidden beyond the event horizon. To explore these mysteries, astronomers turned back to theory simulations and new observations ready to push the Event Horizon Telescope even further. Long before anyone imagined a telescope the size of Earth, Einstein predicted what the region around a black hole should look like. His equations described how gravity warps space, how light bends around massive objects, and how an event horizon marks the boundary where escape becomes impossible. For decades, these predictions were tested indirectly through the orbits of stars, the motion of gas, and the behavior of galaxies, but none of those tests approached the extreme conditions near the edge of a supermassive black hole. That changed with M87. The image provided a direct measurement of the shadow's diameter, and it matched the value predicted by general relativity for a black hole of 6.5 billion solar masses. Any alternative theory of gravity would have produced a different shape, perhaps more elongated, perhaps less stable, perhaps distorted by exotic effects. Instead, the ring was nearly perfect. Its symmetry confirmed that space-time curves smoothly around the black hole, following the geometry Einstein described more than a century ago. Even the brightness asymmetry, where one side of the ring appears more intense, echoed Einstein's insights. Relativity tells us that when matter moves at high speeds, the light it emits becomes brighter in the direction of its motion. This phenomenon called relativistic boosting was not just visible, it was essential to understanding the image. It revealed which side of the disk was rotating toward us, offering clues about the black hole's spin and orientation. The photon ring, the thin boundary where light orbits the black hole before escaping, also matched theoretical predictions. Its position and thickness follow directly from Einstein's equations. Detecting it, even in partial form, strengthened confidence that these extreme environments behave exactly as the theory of general relativity requires. But the confirmation went even deeper. The image constrained exotic ideas about gravity, including theories that attempt to replace the event horizon with new physics. If the black hole had a solid surface or emitted unusual radiation, the shadow would have been smaller or distorted. The smooth circular silhouette suggests that the event horizon is real, a point of no return exactly as general relativity describes. Einstein did not live to see galaxies beyond the Milky Way, let alone the shadow of a black hole. Yet his equations anticipated the behavior of M87's core with remarkable precision. The image was not just a triumph of engineering, it was a moment when the universe itself affirmed the mathematics that predicted its shape. At the center of M87, the black hole does not sit still. It rotates, dragging the fabric of space-time around with it. This spin is one of the most important and most elusive properties of any black hole, because it determines how energy flows, how matter falls inward, and how powerful the surrounding jet becomes. Although we cannot see the rotation directly, the structure of the accretion disk and the stability of the jet reveal clues about how fast the black hole must be spinning. In M87, the evidence points toward a rapidly rotating giant. The jet emerging from its poles has remained aligned for millions of years, suggesting that the black hole's spin axis is stable and strong enough to guide magnetic fields over vast distances. These magnetic fields thread through the plasma in the accretion disk, shaping spirals and filaments that channel energy toward the poles. Near the event horizon, gravity and rotation interact so intensely that magnetic field lines twist into tight bundles, forming a structure capable of launching particles outward at nearly the speed of light. This region, known as the magnetosphere, is one of the most extreme environments in the universe. Here space-time is not merely curved, it is pulled around by the black hole itself. This effect, called frame dragging, forces nearby matter to rotate in the direction of the spin. The faster the spin, the stronger the dragging. In M87, the coherence of the jet suggests that frame dragging is powerful enough to organize the magnetic field into a stable configuration, providing a direct path for energy to escape from the disk. One of the leading theories for how black holes produce jets involves extracting rotational energy from the spin. According to this model, magnetic fields anchored in the disk tap into the black hole's rotation, pulling energy outward in the form of a focused beam. If M87's jet is indeed powered this way, its longevity and brightness imply that the black hole has retained a significant fraction of its original spin throughout cosmic history. The interaction between spin and magnetic fields also affects the appearance of the photon ring. Light rays that skim the event horizon follow paths shaped by the spinning geometry. A rapidly rotating black hole slightly shifts the ring's structure, stretching or compressing it depending on the direction of rotation. Future observations with improved resolution may be able to detect these subtle distortions, offering a more direct measurement of M87's spin. For now, the evidence remains indirect but compelling. The alignment of the jet, the brightness pattern of the ring, and the behavior of the surrounding plasma all point toward a rotating black hole with immense angular momentum. This rotation is not a minor detail, it is a fundamental driver of M87's most dramatic features, linking the invisible physics of the event horizon to structures visible across intergalactic space. Even with an image of its shadow and decades of observations, the black hole in M87 still holds mysteries that challenge the limits of astronomy. The more precisely we measure it, the more questions emerge. Questions that reach far beyond this single object and touch the deepest ideas about how black holes grow, how jets are powered, and whether space-time itself hides layers of physics we've not yet uncovered. One puzzle lies in the stability of the jet. M87's jet has remained aligned for millions of years, a consistency that is difficult to explain. Galaxies undergo mergers, absorb matter from their surroundings, and experience internal turbulence. All of these processes can torque a black hole and shift its orientation, yet the jet from M87 has barely drifted, suggesting either an unusually calm history or a mechanism that holds the spin axis tightly in place. Understanding this stability could reveal how black holes interact with the galaxies that host them. Another open question concerns the black hole's spin. Current data suggests rapid rotation, but the exact rate remains uncertain. Measuring spin directly requires finer resolution of the photon ring, a task that will demand a more powerful event horizon telescope, possibly including radio dishes in orbit or on the moon. The spin not only shapes the jet, but also encodes the history of how M87 grew. A high spin implies steady directed accretion. A lower spin might hint at chaotic growth, including mergers with other black holes. Determining the spin would allow astronomers to reconstruct M87's ancient past. There is also the question of how the accretion disk behaves at scales smaller than we can currently resolve. Turbulence near the event horizon drives magnetic instabilities that govern how matter falls inward, but these processes operate on distances far too small for today's telescopes to observe. Simulations attempt to capture this microphysics, but only sharper images, true movies of plasma orbiting the black hole, will reveal what is really happening in that chaotic luminous environment. The structure of the photon ring itself remains a frontier. In theory, the ring should consist of multiple nested layers created by photons looping around the black hole several times before escaping. The first EHT image captured only the outermost layer. Detecting the deeper rings would test general relativity with unprecedented precision, pushing the theory into a regime where even tiny deviations could signal new physics. Whether these inner rings exist exactly as predicted, or whether they hide subtle surprises, is one of the most important questions the next generation of telescopes may answer. Finally, there is the matter of long-term evolution. Will M87 continue feeding its central black hole? Will the jet remain active for another million years? Could a future merger disrupt the alignment we see today? And how will the surrounding galaxy respond to the energy pouring out of the core? These questions remind us that ES-7 is not static. It is a system still evolving, still interacting with its environment, still shaping the cluster around it through gravity and radiation. M87 has already revealed more than we once believed possible, but it has not surrendered its secrets. Each answer it offers points toward deeper layers of complexity, layers waiting for new instruments, new observations and new ideas to uncover. The black hole in M87 did more than confirm what astronomers expected. It changed the scale and precision of what we can know. Before 2019, black holes were understood through indirect evidence: the motion of stars, the glow of hot gas, the power of jets, or the gravitational waves produced when two black holes collided. These methods prove that black holes exist, but none revealed what the boundary around them actually looks like. M87 provided that missing piece. For the first time, the silhouette of an event horizon was measured with enough clarity to test gravity in its strongest form. The shadow's size matched the predictions of general relativity within a few percent, ruling out many alternative theories. Models that suggested quantum structures or exotic surfaces at the edge of a black hole were pushed into tighter constraints. The result was a kind of certification. Black holes behave the way Einstein's mathematics says they should, even at the edge where space-time folds in on itself. M87 also changed our understanding of black hole growth. Its enormous mass and stable jets showed that supermassive black holes can remain active for millions of years, shaping their galaxies over cosmic timescales. The jet affects how gas cools, how stars form, and even how matter is distributed throughout the Virgo cluster. This demonstrated that black holes are not passive objects. They regulate their environments, sometimes suppressing star formation, sometimes triggering it, and always influencing the structure of the space around them. The techniques developed for observing M87 sparked a new era of imaging black holes. The Event Horizon Telescope has since expanded, with more observatories joining the network, and plans to add space-based antennas that could increase resolution by an order of magnitude. These upgrades may allow scientists to detect the swirling motion of plasma near the event horizon. Not just a static image, but a sequence of frames revealing the dynamics of light in extreme gravity. Data from M87 also reshape the study of black hole spin magnetic fields and accretion physics. Researchers now use the image as a benchmark for simulations, testing how different models reproduce the observed ring. This calibration has improved our understanding of how jets are launched and how energy is extracted from rotation. The black hole has become a standard reference point, a kind of a laboratory in space that anchors theories across astrophysics. Perhaps the most profound shift lies in public imagination. Black holes have long captured curiosity, but the image of M87 transformed them from abstract concepts into observable structures. It provided a bridge between theory and sight, turning an invisible region of space-time into a concrete shape. We could measure, analyze, and compare with predictions. It is rare for an astronomical image to redefine both science and culture, but M87 achieved that, making the unseen visible and the unimaginable real. Across 50 million light-years, the light that escaped from the edge of M87's black hole has travelled longer than our species has existed. It crossed the space between galaxies, slipped through clusters of stars, and finally reached Earth as a faint signal captured by dishes pointed at the sky. In that signal, encoded within a pattern of radio waves, was a shape that once seemed impossible to see, a shadow cast by gravity itself. What makes the image extraordinary is not only that it revealed the boundary of a black hole, but that it allowed us to trace the path of light as it bent through warped space-time. The glowing ring is the last testimony of photons that skimmed the surface of the event horizon before escaping outward. They carry with them the story of a place where the laws of nature reach their most extreme form. When we look at that ring, we are seeing the imprint of gravity operating at its limit. M87 stands as a reminder that the universe hides structures far larger and more powerful than anything in our own galaxy. Its central black hole has consumed star-shaped gas flows and launched a jet visible across intergalactic distances. It has influenced the evolution of the Virgo cluster, carving a mark into the architecture of space that will last for millions of years. Yet despite its immense presence, the black hole remains silent and unseen except through the light spiraling around it. The first image was not the end of the story. It was the opening of a new era. As the Event Horizon telescope grows, astronomers hope to sharpen the ring, capture the motion of plasma near the event horizon, and perhaps detect the deeper layers of the photon ring. These efforts will turn a still image into something closer to a living view, a window into the behavior of matter and light in the most extreme environment known to physics. And so the black hole in M87 becomes more than a distant object. It becomes a reference, a guide, a point where theory and observation converge. It shows us that even in the deepest shadows of the universe there is structure, there is order, there is light shaped by gravity into forms that follow the rules of space-time itself. When we look at M87, we are not just seeing a black hole, we are witnessing the universe revealing one of its secrets, the shape that light takes when it dances at the edge of oblivion. And in that shape across millions of light years, we find a reminder of how much more there is still left to see. 25,000 light years from Earth, hidden behind a thick curtain of dust and glowing gas, lies the most mysterious region of the Milky Way. It is a place where stars move with impossible speed, where radiation pulses unpredictably, and where the very structure of space-time seems to twist beneath an invisible force. To the naked eye, the center of our galaxy looks empty, a dark gap in a river of starlight. But astronomers have learned that this darkness is only an illusion. Beneath it sits something extraordinary. At the exact core of the Milky Way rests Sagittarius A, a supermassive black hole 4 million times the mass of the Sun. It is the closest black hole of its kind, yet it remains one of the most difficult objects in the sky to observe. Dust absorbs visible light, gas clouds block the view, and the region is so crowded with stars that even advanced telescopes struggle to isolate individual objects. For decades, astronomers could only infer that something massive was hiding there, something compact, heavy, and powerful enough to dominate the motion of everything nearby. The first clues came from the way stars behaved deep in the galactic center. They looped around an unseen point with astonishing velocity, tracing orbits so tight and fast that no ordinary object could possibly lie at their focus. The faster the stars moved, the clearer the message became. At the heart of our galaxy, something immense was shaping the dance of millions of suns. Yet the true nature of Sagittarius A remained hidden, locked behind the thickest dust clouds in the Milky Way. To uncover it, astronomers would need to look through wavelengths of light invisible to human eyes, track stars across decades, and apply the most precise measurements ever attempted in galactic astronomy. What they found would transform our understanding of gravity, black holes, and the structure of the galaxy we call home. The center of the Milky Way is one of the most extreme regions in our galaxy. Unlike the calm spiral arms where our sun resides, the galactic core is crowded, turbulent, and wrapped in layers of interstellar dust so dense that visible light cannot escape. Through an ordinary telescope, this region appears as a dark void, a gap carved across the bright band of the Milky Way. But when astronomers observe it in infrared and radio wavelengths, the darkness dissolves, revealing a landscape more chaotic than anywhere else in the galaxy. This hidden zone is known as the Galactic Center, a region only a few light years wide that contains some of the most densely packed stars ever observed. Many of them are young, massive, and burning violently despite the harsh conditions. Their presence is itself a mystery. No textbook model predicts stars forming easily in such a hostile environment, yet the core is filled with them. Infrared images show them scattered around a compact, bright hub of radiation. The location of Sagittarius A, gas clouds swirl through the area in long filament-like structures. Shockwaves from stellar winds and supernova explosions ripple through the core, heating gas to millions of degrees. Powerful magnetic fields twist through the region, shaping the flow of charged particles and creating arcs of radio emission that trace the underlying structure. Every observation of the galactic center reveals new patterns of motion, new layers of complexity, and new signs that something enormous lies at the middle of it all. Radio maps show a compact source no wider than the orbit of Mercury, producing flickers of emission that change from hour to hour. This source, Sagittarius A, stands out sharply from its surrounding. Nothing else in the region is so small and yet so energetic. It releases bursts of infrared and X-ray light that flare unpredictably, suggesting matter is falling inward, heating up and then vanishing into an unseen gravitational well. The behavior is too compact, too hot, and too variable to match any known star or stellar remnant. Still, in the early years of study, astronomers hesitated. The galactic center is crowded enough that multiple objects can appear fused in coarse images. Could Sagittarius A be a cluster of dim stars? Could it be a cloud of dense gas? Or even a collection of neutron stars orbiting a shared center of mass? These possibilities lingered because no instrument could yet resolve the motions of individual stars within the core. That changed when observatories turned to infrared adaptive optics and long-term monitoring campaigns. For the first time, astronomers were able to watch the stars near Sagittarius A move with unprecedented clarity. Their motions would soon reveal the identity of the hidden giant and settle one of the biggest mysteries in modern astrophysics. The breakthrough began when astronomers finally succeeded in isolating individual stars orbiting the center of the Milky Way. Using the Keck Observatory and the Very Large Telescope equipped with advanced adaptive optics to counteract atmospheric distortion, researchers could track the positions of stars packed densely around Sagittarius A with extraordinary precision. What they discovered was astonishing. These stars were not drifting gently like those in the spiral arms. They were racing. Some moved faster than any star previously observed, reaching thousands of kilometers per second as they curved around an unseen point. Their orbits were tight, sharply bent, and completed over periods far shorter than anyone expected for stars so close to the galactic core. It was as if an invisible hand were pulling them inward, forcing them to swing around a central mass with incredible speed. Two research teams led independently by Reinhard Genzel and Andrea Ghez began long-term monitoring campaigns, returning year after year to record the changing positions of these stars. They soon found that the motions were not random. Each star followed a smooth, predictable path, an orbit shaped by gravity alone, and all of the orbits pointed to the same conclusion. The stars were revolving around a single compact object with a gravitational pull far greater than any cluster of stars or neutron stars could produce. The region controlling their motion was unimaginably small. The stars traced ellipses around a point no larger than our solar system, yet containing 4 million times the mass of the Sun. Such a concentration of matter ruled out every alternative explanation. A cluster of stars would collapse or scatter. A cloud of dark objects would destabilize. Only one idea remained consistent with the data: a supermassive black hole. The behavior of these stars provided the first compelling dynamical evidence that Sagittarius A was exactly that. Each measurement tightened the constraints, shrinking the allowed space for any competing hypothesis. Year after year, as more stars completed their arcs, the story solidified. Whatever lay at the center of the Milky Way had to be massive, compact, and gravitationally dominant in a way no ordinary matter could replicate. Yet the most dramatic piece of evidence was still to come. The orbit of a star whose full journey around Sagittarius A would reveal the black hole's existence beyond all reasonable doubt. Among all the stars racing around the center of the Milky Way, one stood out above the rest. It was a bright, fast-moving star, later named SS2, a young, massive object, orbiting closer to Sagittarius A than any star ever observed. Tracking S2 became a mission that would span decades because its orbit promised something extraordinary: the first complete map of a star circling a supermassive black hole. S2 follows an elongated 16-year orbit that carries it deep into the gravitational well of Sagittarius A. As astronomers traced its path across the sky, they watched it swing inward, accelerate, and whip around the invisible center with breathtaking speed. At the point of closest approach, S2 came within roughly 120 astronomical units of Sagittarius A, only a few times the distance between the Sun and Pluto. At that moment, it reached a velocity of nearly 8,000 kilometers per second. No ordinary massive object could make a star move that fast without tearing it apart. The data were unambiguous. All the motion, every twist of the orbit, every shift in velocity pointed to a single conclusion. S2 was circling a compact mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. Alternatives collapsed under the weight of the numbers. A cluster of neutron stars would scatter within a single orbit. A cloud of dark objects would collapse under its own gravity. Even exotic theoretical constructs lacked the stability needed to explain S2's trajectory. As S2 completed its closest passage in 2002, and again in 2018, astronomers captured something even more remarkable: the effects of general relativity in real time. Light from the star became stretched and reddened as it passed through the intense gravitational field of Sagittarius A, a direct confirmation of Einstein's predictions. The orbit itself did not close perfectly, instead processing just as relativity demanded. The star was not following Newton's gravity. It was tracing the curvature of space-time. By the time S2 completed its full orbit, the case was sealed. This was undeniable proof of a supermassive black hole at the center of the Milky Way. No other explanation matched the precision of the observations. The motions of S2 and the other nearby stars transformed Sagittarius A from an intriguing hypothesis into one of the best measured black holes in the known universe. And now that the black hole's existence was certain, a new question emerged. What exactly was Sagittarius A, and why was it so different from monsters like the one in M87? Sagittarius A is unlike the monstrous black holes found in distant galaxies. It is smaller, quieter, and far less dramatic than the titanic engines that power quasars, and yet its modest appearance hides one of the most precisely measured black holes in the universe. With a mass of roughly 4 million suns, it occupies a region so compact that the entire event horizon would fit inside the orbit of Mercury. Everything near it, gas dust, stars, and magnetic fields, feels its pull. Yet from Earth, it remains invisible behind clouds of interstellar dust. What makes Sagittarius A especially fascinating is how little it consumes. Most supermassive black holes are surrounded by bright accretion disks feeding on gas that spirals inward and heats to enormous temperatures. Sagittarius A has no such blazing disk. The environment around it is sparse, with only thin streams of hot gas drifting close enough to be captured. Because it receives so little material, the black hole emits only faint bursts of infrared and X-ray radiation, making it one of the dimmest supermassive black holes astronomers have ever studied. This quiet nature once raised doubts about whether Sagittarius A was a black hole at all. Could a cluster of dark stellar remnants mimic its gravity without producing strong radiation? The answer became clear once S2 and other nearby stars were tracked. No cluster of objects could remain so compact without tearing itself apart. The mass at the center had to be confined within a tiny volume, far smaller than any known star, neutron star, or exotic structure could support. Only a black hole fit the data. Despite its low activity, Sagittarius A is not completely dormant. Occasionally a pocket of gas drifts too close and is heated to tens of millions of degrees, producing brief flares that brighten the region for minutes or hours. These events are unpredictable, like sparks popping from a hidden fire, giving astronomers rare glimpses into the behavior of matter just before it crosses the event horizon. Each flare is a reminder that even the calmest black holes can stir when the right material falls inward. The quiet environment also allows nearby stars to survive in surprisingly close orbits. In more active galaxies, the intense radiation from the accretion disk can strip atmospheres, disrupt stellar orbits, or tear apart passing objects. Sagittarius A, by contrast, exerts its power mainly through gravity. It holds the core of the Milky Way together, anchoring the orbits of stars across tens of thousands of light years. Yet it does so without the violent outbursts seen elsewhere. Sagittarius A is the black hole we can study in the most detail, because it's both massive enough to reveal the curvature of space-time and calm enough to let stars orbit safely around it. It is not a quasar, not a cosmic lighthouse, but a silent giant, the gravitational heart of our galaxy. Capturing the shadow of Sagittarius A was far more difficult than imaging the black hole in M87. Even though Sagittarius A is much closer to Earth, its event horizon appears only slightly larger on the sky, equivalent to seeing a donut on the surface of the Moon. But the real challenge was not its size, it was its speed. Material orbiting Sagittarius A moves so quickly that the appearance of the accretion flow changes from minute to minute. While M87 remains stable over days, Sagittarius A flickers and shifts continuously. Its plasma swirls like boiling water, brightening, dimming and reshaping itself faster than any telescope can freeze into a single frame. For the Event Horizon telescope, which must combine hours of data into a coherent image, this variability made the target extraordinarily difficult. The array observed Sagittarius A using the same Earth-sized network of radio telescopes that captured M87, but this time the data looked different. Instead of a stable structure, the signals fluctuated rapidly. Algorithms had to compensate for motion in the source itself, reconstructing not a single static picture, but an average of countless evolving states. It was as if photographers were trying to capture a clear portrait of someone who never stopped moving. Despite these challenges, the shadow emerged. In May 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. The ring was softer and more irregular than M87's, but its size matched the predictions for a 4 million solar mass black hole with remarkable precision. The diameter of the shadow confirmed the mass derived from stellar orbits. The shape matched the curves expected from light skimming the edge of a black hole's gravitational well. This image was more than a technical milestone. It proved that the methods used to capture M87 could be pushed into even more unstable regimes. It showed that black holes, despite their differences in size and environment, obey the same underlying geometry predicted by general relativity, and it provided a second anchor point, a second silhouette for testing gravity at its strongest. Unlike M87, Sagittarius A does not produce a giant jet or flood its surroundings with radiation. Its image is faint, subtle, and shaped by rapid turbulence, yet it marks one of the most important achievements in modern astronomy. Direct visual evidence of the black hole at the center of our own galaxy, seen across a veil of dust that once hid it completely. One of the most surprising things about Sagittarius A is how little light it produces. For a black hole sitting at the center of a large galaxy, its brightness is astonishingly low. Instead of blazing like a quasar or erupting with powerful jets, Sagittarius A emits only faint whispers of X-rays and radio waves. The reason is simple but profound. It barely has anything to eat. Most supermassive black holes grow by devouring gas that spirals inward in a bright, violent accretion disk. As the gas compresses and heats, it radiates enormous amounts of energy, but the environment around Sagittarius A is unusually sparse. Stellar winds push material in many directions, and much of the gas near the center has too much angular momentum to fall inward. The result is a starvation regime, a black hole with a huge gravitational appetite but almost nothing available to consume. Even when material does approach Sagittarius A, much of it fails to reach the event horizon, Simulations suggest that only a small fraction of incoming gas actually crosses the boundary. The rest is heated, stirred, and then expelled back into space by turbulence and magnetic fields. This inefficient feeding process explains why the black hole shines so weakly compared to giants like M87. But the dimness of Sagittarius A is not a sign of inactivity. Every so often, a cloud of gas drifts too close and triggers a brief flare. These flares can increase the black hole's brightness by factors of hundreds, for a short time illuminating the region in infrared and X-ray wavelengths. The outbursts last minutes or hours before fading again, providing rare glimpses of the material spiraling near the event horizon. Each event acts like a flash of lightning, revealing the contours of an otherwise invisible structure. Its quiet behavior has also allowed stars to orbit astonishingly close without being stripped or destroyed. In more active galactic nuclei, the radiation from the accretion disk can heat or destabilize nearby systems. Sagittarius A, by contrast, influences its surroundings primarily through gravity. The lack of intense radiation has allowed the nuclear star cluster, the dense grouping of stars around the core, to survive and continue orbiting without disruption. This subdued personality makes Sagittarius A an exceptional laboratory. It offers a clean environment for studying gravity near a black hole, without the overwhelming glare of a luminous disk. It is both massive enough to warp spacetime in ways we can measure and quiet enough that stars can trace smooth orbits through its gravitational field. In the language of astrophysics, Sagittarius A is a rare balance point, a dormant supermassive black hole that still reveals the pure geometry of gravity. In the early 2000s, astronomers noticed something strange moving towards Sagittarius. A small, faint object that did not behave like any star. It appeared as a cloud of gas drifting along a highly elongated orbit destined to make a dangerously close pass near the black hole. This object was labeled G2, and many expected it to be torn apart as it approached the event horizon. For months, predictions circulated that Sagittarius A might flare dramatically when the cloud was shredded and swallowed. But when G2 finally reached its closest approach in 2014, nothing dramatic happened. The cloud stretch slightly brightened briefly in infrared light, and then continued past the black hole mostly intact. It did not fragment, did not evaporate, and did not feed a major outburst. Instead, it behaved as if something inside were holding it together. This unexpected resilience forced astronomers to reconsider what G2 really was. One idea quickly gained traction. G2 might not be a cloud at all, but a star wrapped in a thick envelope of dust and gas. If a pair of stars had recently merged, a surprisingly common event in the dense galactic center, the resulting object could produce a swollen shell of material that looks and moves like a gas cloud. Such an object would appear fragile from the outside, but remain gravitationally bound on the inside, explaining why G2 survived the close encounter. Then came an even stranger discovery. A second object, G1, exhibited almost the same behavior and nearly identical orbital characteristics. Both G1 and G2 followed similar paths, raising the possibility that they belong to a larger family of such objects, remnants of stellar mergers populating the region around Sagittarius A. If true, the galactic center may be filled with stars in transitional states, their outer layers puffed out by violent interactions before slowly contracting over time. These unusual bodies are more than curiosities. Their orbits probe the gravitational field just outside the event horizon, offering clues to the black hole's mass and the distribution of matter around it. Their resilience also provides insight into how stars form, merge, and evolve under the extreme conditions near Sagittarius A. Each close passage acts as a natural experiment, testing whether gas clouds, dust shells, and unstable stellar remnants can survive the tidal forces near a supermassive black hole. The flares that occasionally accompany these encounters add another layer to the puzzle. When material is stripped from objects like G2, even in small amounts, it can fall inward and heat to millions of degrees, producing brief flashes of light. These flares are valuable because they reveal the behavior of matter in the final moments before crossing the event horizon, moments that cannot be captured by steady imaging alone. Together, G1, G2 and the other odd objects near the Galactic Center highlight how dynamic and unpredictable this region truly is. While Sagittarius A appears quiet from afar, its surroundings are anything but. Strange bodies drift inward, stars interact and collide, and gas clouds weave among them, creating a constantly shifting environment that still defies full explanation. Sagittarius A and the black hole in M87 sit as opposite ends of the supermassive black hole spectrum. They are built from the same physics, shaped by the same geometry of space-time, yet they behave in dramatically different ways. Understanding one requires understanding the other, because each reveals what black holes can become under different cosmic conditions. M87 is a Titan, a 6.5 billion solar mass monster, surrounded by a dense energetic disk of hot plasma. It devours material at a steady rate, lighting up its core and launching a relativistic jet that stretches across thousands of light years. Its mass flattens space-time into broad, deep curves. Processes around it evolve slowly, sometimes taking days or even years to change in ways we can detect. For a telescope like the Event Horizon Telescope, this stability is a gift. The environment is violent but steady, producing a nearly perfect ring of light around the shadow. Sagittarius A, in contrast, lives in a different regime. With only 4 million solar masses, it's far smaller, far dimmer, and far more chaotic on short timescales. Matter around it orbits so quickly that the brightness shifts minute by minute. Instead of a towering jet, it produces brief flares that flicker and fade almost as soon as they appear. For observers, this rapid variability makes Sagittarius A a moving target, harder to image, harder to model, and far more sensitive to small changes in its environment. Yet the two black holes share something profound: the shape of their shadows. Despite the size difference, both display a ring whose diameter matches the predictions of general relativity with striking precision. This agreement shows that the geometry of space-time near a black hole depends primarily on mass and spin, not on the environment around it. Whether surrounded by a roaring accretion disk or a thin stream of gas, the curved space at the event horizon follows the same mathematical rules. Comparing the two also reveals how black holes influence their galaxies. M87 acts like a cosmic engine, injecting energy into the surrounding cluster and regulating how stars form over vast regions. Sagittarius A plays a quieter role, anchoring the Milky Way with gravitational stability, but exerting little influence beyond the central few light years. One sculpts the behavior of an entire galaxy cluster. The other quietly maintains the balance at the heart of a single spiral galaxy. The contrast highlights how environment, not just mass, shapes a black hole's personality. Given enough fuel, even Sagittarius A could flare into a quasar. Given less, even M87 would dim into silence. What we see today is a snapshot shaped by history, the paths each galaxy followed, the mergers they experienced, and the gas reservoirs they inherited. Together, Sagittarius A and M87 form a natural pair of reference points. One shows the extreme of stability and power. The other reveals the subtle geometry of gravity in a quiet environment. Both deepen our understanding of how black holes live, evolve, and sculpt the universe around them. At the center of the Milky Way, hidden behind a veil of dust that has blocked human eyes for all of history, lies a place we can only understand through careful measurement and the faint glow of invisible light. Sagittarius A does not roar like a quasar or carve the sky with a jet. It waits in silence, shaping the motion of stars and anchoring the spiral form of our galaxy without ever announcing its presence. It is the quiet heart of the Milky Way, a gravitational anchor that has influenced the structure of our cosmic home for billions of years. From Earth, the distance and obscuring dust make the Galactic Center look empty, a dark wound in a river of starlight. Yet every observation reminds us that the darkness is full. Stars move in tight arcs. Gas clouds stretch and twist. and bursts of infrared light flicker as material skims the boundary of the event horizon. Even in its calmest state, Sagittarius A shapes everything around it. The image captured by the Event Horizon Telescope was more than a technical triumph. It was a revelation, a glimpse of the shadow cast by a black hole we've lived beside for our entire existence. The soft ring of light is not a portrait in the ordinary sense. It is the last signal from photons that orbited the edge of gravity's deepest well before escaping across 25,000 light-years to reach us. In that faint blurred glow, we saw the first evidence of the geometry at the core of our own galaxy. Sagittarius A is a reminder that extraordinary structures lie hidden even within familiar places. The Milky Way, with its gentle arms and quiet night sky, holds a supermassive black hole at its core, not destructive but essential. Without it, the galaxy's central region would not be bound as it is. The long-term stability of the Milky Way depends on the very object we cannot see. As instruments continue to advance, astronomers hope to watch the motion of plasma near the event horizon in real time to capture sharper images and to reveal the deeper layers of the photon ring predicted by theory. In the coming decade, Sagittarius A may shift from a blurred silhouette to a dynamic window into the nature of gravity itself. For now, we see only a dim ring and the orbits of a few courageous stars that venture close enough to trace the invisible. But in those arcs and flashes, the heart of our galaxy becomes visible at last, not through light, but through the way light bends curves and finally escapes. Sagittarius A is the quiet center of a galaxy that holds billions of worlds, including ours, and in the stillness of its shadow we glimpse the structure that has shaped our cosmic home from the beginning. More than 10 billion light-years away in a region of the universe that existed when galaxies were still young, a single point of light blazes brighter than entire clusters of stars. It shines with such intensity that its glow crosses the expanding fabric of the cosmos, reaching Earth after a journey longer than the age of our solar system. That light comes from a quasar known as TON 6181, one of the most extreme and powerful objects ever discovered. At first glance, TON 618 looks like a star, just a tiny speck in the sky. But it is nothing like a star. It is the brilliant signature of a supermassive black hole consuming matter at a furious rate. Around it, gas spirals inward at nearly the speed of light, heating to temperatures that make even the core of a star seem cold. This radiant furnace produces more energy than thousands of Milky Way galaxies combined, and hidden beneath that radiance lies the true monster, a black hole with a mass of roughly 66 billion suns. The light we see today began its journey when the universe was only a few billion years old. It has been stretched, dimmed, and shifted by cosmic expansion, yet it still arrives with a message about a time when conditions were radically different from the universe we inhabit now. TON 618 is not merely distant, it is ancient. It shows us a glimpse of the early cosmos when black holes were growing at rates that challenge everything we think we know about how these giants form. How did something so massive rise so quickly? How could a black hole reach such an extraordinary size in the short time available after the Big Bang? And what does its incredible brightness reveal about the physics of accretion radiation and gravitational growth during the universe's formative years? The answers lie in the blazing disk that surrounds the black hole in the spectra, carried by its light, and in the history of the quasar itself. TON 618 is more than a cosmic landmark. It is a puzzle, one that forces us to rethink the limits of gravity, the behavior of matter at extreme scales, and the speed at which the universe can build its most colossal structures. TON 618 is classified as a hyperluminous quasar, a type of active galactic nucleus powered by a supermassive black hole feeding at an extraordinary rate. Seen from Earth, it appears as a brilliant star-like point, but its true nature becomes clear only when its light is separated into a spectrum. Instead of the narrow familiar lines of a star, its spectrum shows immense broadened emission features, the unmistakable signature of gas moving at tens of thousands of kilometers per second around a massive black hole. A quasar forms when gas falls into the gravitational grip of a central black hole and spirals inward through a vast accretion disk. Friction and magnetic turbulence heat the disk to extreme temperatures, causing it to radiate across the entire electromagnetic spectrum. In TON 618, this disk is so luminous that it overwhelms the host galaxy, outshining every star within it. The energy released is greater than the combined luminosity of thousands of Milky Way-like galaxies. It is a beacon that cuts through the early universe, marking a place where matter is being devoured on a scale almost beyond imagining. The distance to TON 618 is another crucial part of its identity. With a redshift of nearly 2.2, the light we observe today shows the quasar as it existed more than 10 billion years ago. That places it in a cosmic era when galaxies were forming. Rapidly, stars were being born in enormous numbers, and black holes were growing at rates far higher than they do now. TON 618 belonged to that youthful universe, a time when conditions allowed for the birth of giants. Its central black hole, weighing roughly 66 billion suns, places it among the most massive black holes ever detected. Only a handful of known quasars approach this scale, and even fewer exceed it. For perspective, the black hole at the centre of the Milky Way is 4 million solar masses. The one in M87 is 6.5 billion. TON 618 dwarfs them both. Its mass challenges existing theories of how quickly black holes can grow, forcing astronomers to reconsider the initial seeds and accretion processes that operated in the early universe. TON 618 is not merely bright, it is physically enormous, gravitationally dominant, and cosmologically significant. It represents a type of quasar that pushes physical processes to their limits. A rare example of what happens when a black hole grows rapidly in a universe still rich with pristine gas. Everything about it is an invitation to dig deeper to understand how such an extreme object could have formed so early in cosmic history. TON 618 did not enter astronomy with fanfare. It began as a faint, unremarkable entry in an old photographic survey carried out by the Tonantzintla Observatory in Mexico. In those early catalogues, it was simply another blue object on the sky, a point of light that looked like a star but behaved just differently enough to raise questions. At the time, quasars were still new to science. Their true nature was not yet understood, and many astronomers were still grappling with the idea that seemingly star-like objects could be located billions of light-years away. As surveys improved, TON 618 attracted more attention. It was reobserved during the Palomar Sky Survey, and its brightness across ultraviolet wavelengths immediately stood out. Unlike ordinary stars, it emitted far too much high-energy radiation. Its light did not match any familiar spectral pattern. Something powerful was hiding behind that pinpoint glow. The breakthrough came when its spectrum was measured in detail. Instead of narrow absorption lines typical of a star, TON 618 displayed enormous emission features broadened by gas moving at tremendous speeds. These broad lines are the hallmark of a quasar gas clouds orbiting a supermassive black hole at thousands of kilometers per second. But there was another clue hidden in the spectrum. Nearly all of the emission lines were shifted to longer wavelengths. That redshift revealed its staggering distance. With a redshift of nearly 2.2, TON 618 was located more than 10 billion light-years away. The faint point of light on a survey plate was not a star at all. It was the blazing core of a galaxy from the early universe powered by a black hole that dwarfs almost every other known object of its kind. Once its distance was established, its luminosity became impossible to ignore. The quasar was emitting enough energy to outshine thousands of Milky Way-like galaxies. If the light were coming from an ordinary star, it would have needed to be impossibly bright, brighter than physics would permit. The only explanation was a supermassive black hole drawing in matter at extreme rates and converting gravitational energy into radiation. TON 618 quickly rose from obscurity to become one of the most intriguing quasars ever identified. Its combination of immense distance, overwhelming brightness, and extreme spectral features made it a benchmark object in the study of quasar physics. But the true surprise would come later when astronomers attempted to measure the mass of the black hole at its centre, a calculation that would elevate TON 618 from bright quasar to cosmic titan. At the heart of TON 618 lies an engine so powerful that it can be detected across more than 10 billion light-years of expanding space. This engine is the accretion disk, a vast rotating structure of superheated gas spiraling into the gravitational grip of the central black hole. Nothing in the modern universe rivals the intensity of a quasar's accretion disk, and TON 618 pushes that intensity to the very edge of what physics allows. Gas falling toward the black hole does not plunge straight in. Instead, it forms a disk compressed and stirred by turbulence and magnetic fields. As friction heats the gas, its temperature rises into the millions of degrees, causing it to emit radiation across the entire electromagnetic spectrum. In TON 618, the disk is so luminous that it outshines its host galaxy by orders of magnitude. Every second, colossal amounts of matter release gravitational energy in the form of ultraviolet light X-rays and high-frequency radiation that flood the surrounding space. The brightness of this disk reveals how quickly material is being swallowed. Quasars cannot shine indefinitely at extreme levels because too much radiation pushes back on incoming gas, creating a natural limit known as the Eddington rate. TON 618 appears to be operating near that limit, a sign that the black hole is feeding at one of the highest sustainable rates in the universe. This regime is rare today, but in the early cosmos, when gas was abundant and galaxies were still forming, such accretion was far more common. Surrounding the disk is the broadline region, a chaotic cloud of gas orbiting at staggering speeds. At TON 618, these velocities reach tens of thousands of kilometers per second. As the gas races through the intense radiation field, it lights up with emission lines that stretch and blur across the spectrum. These features are the fingerprints astronomers use to estimate the black hole's mass, and in the case of TON 618, those fingerprints pointed to something astonishing. The disk, the radiation it emits, and the swirling ocean of gas surrounding it all serve as evidence of the immense gravitational force at the center. Every photon escaping the quasar carries information about the environment, where it formed a region governed by extreme temperatures, powerful magnetic fields, and velocities approaching the speed of light. TON 618 is not simply bright. It is a furnace operating at the highest efficiency nature can achieve, converting mass into energy with uncanny precision. What makes the quasar even more remarkable is that it has likely been active for an extended period. Sustaining such intense brightness requires a continuous flow of material. In the early universe, that flow was provided by vast reservoirs of primordial gas funneled through the young galaxy. The accretion disk we see today is the latest phase of a long, violent history of growth, a history written in the lines of the spectrum and the power of the radiation that now reaches Earth. This engine is the reason TON 618 dominates its corner of the early universe, but the true scale of the monster driving it would only become clear when astronomers attempted one of the most difficult measurements in astrophysics, weighing a black hole that cannot be seen directly. Weighing a black hole is never simple. We cannot place it on a scale and we cannot observe its surface, but we can measure how its gravity affects the matter around it. In the case of TON 618, the only information we have comes from the light emitted by gas orbiting at tremendous speeds in the quasar's inner regions. That light carries the imprint of the black hole's mass if we know how to interpret it. The key lies in the broadline region, a chaotic halo of ionized gas swirling above the accretion disk. In TON 618, this gas moves so fast that its spectral lines become enormously stretched. Instead of appearing as thin, precise features, they expand into wide, smeared structures, evidence of velocities exceeding tens of thousands of kilometers per second. These speeds are not arbitrary. They are controlled entirely by the gravitational pull of the central black hole. The stronger the gravity, the faster the gas must orbit to remain bound. Astronomers use this behavior to estimate the mass through a method known as virial analysis. By measuring how broad the emission lines are, essentially how fast the gas is moving, and combining that with the estimated distance of the gas from the black hole, they can infer the mass needed to hold the region together. For ton 618, the numbers point to something extraordinary. The width of the lines is immense, far larger than in typical quasars, indicating orbital speeds at the very limit of stability. When the calculations are performed, the result is a mass of roughly 66 billion suns. Independent surveys reach similar values, strengthening the conclusion. The consistency across different techniques, from ultraviolet line analysis to comparisons with other hyperluminous quasars, suggests that ton 618's mass is not an overestimate. Instead, it represents a genuine outlier, one of the largest and most extreme black holes ever identified in the observable universe. Only a handful of candidates exceed 50 billion solar masses, and ton 618 stands at the top of that short list. What makes this measurement even more remarkable is its age. The black hole we observe formed and grew within the first few billion years of cosmic history. For a black hole to reach such an extraordinary size in such a short time challenges every standard model of black hole evolution. It suggests either that ton 618 began as a massive seed, perhaps tens or hundreds of thousands of solar masses, or that it experienced an extended period of nearly uninterrupted high-efficiency accretion. The mass also explains the quasar's extreme brightness. A heavier black hole has a larger gravitational well and a more powerful accretion disk capable of releasing greater amounts of energy. Ton 618's luminosity is therefore a direct consequence of its tremendous mass, and understanding one provides insight into the other. But knowing the mass is just the beginning. The real puzzle is how the universe allowed such a giant to form so early. Did ton 618 follow an unusual growth path? Or does its existence reveal that the early universe was more hospitable to black hole giants than we ever imagined? These questions lead directly into one of the deepest mysteries of modern astrophysics: how a black hole can become this massive in such a short amount of cosmic time. The most unsettling fact about ton 618 is not its mass, it is when that mass existed. The light we see today left the quasar when the universe was little over 3 billion years old, barely a quarter of its current age. In cosmic terms, this is childhood. Structures were still forming, galaxies were merging rapidly, and the first generations of stars were only beginning to enrich the universe with heavy elements. Yet somehow in this turbulent young cosmos, a black hole grew to a size that defies ordinary astrophysical processes. Under typical conditions, black holes grow slowly. Even with a steady supply of gas, the energy they emit pushes outward on the incoming matter, creating a natural speed limit known as the Eddington rate. If a black hole accretes faster than this limit for long periods, the radiation pressure should blow away the fuel before it can fall inward. That rule works well for most black holes in the modern universe. But ton 618 seems to have surpassed what those rules predict. To reach roughly 66 billion solar masses so early, several extraordinary pathways are possible. The first involves the birth of a massive seed. Instead of forming from a collapsing star, ton 618 may have begun as a black hole created directly from the collapse of a primordial gas cloud in the early universe. These direct collapse black holes could have initial masses tens or even hundreds of thousands of times that of the Sun. If ton 618 started this big, it had a head start one that would allow it to grow rapidly through accretion. Another possibility is that the black hole experienced phases of super Eddington growth. Under certain extreme conditions, dense gas flows can fall inward so quickly that the outward radiation does not have time to push them away. Simulations suggest that in the chaotic early universe such flows may have occurred frequently. If ton 618 had access to streams of pristine hydrogen funneled directly into its core, it could have grown at extraordinary rates without breaking physical laws. There is also the possibility of mergers. Galaxies in the early universe collided often, and these collisions can bring central black holes together. If TON 618's host galaxy formed through a chain of early mergers, its central black hole may have absorbed multiple predecessors, each adding millions or billions of solar masses. Such a history would be violent, luminous, and incredibly efficient at producing giants. But even combining these scenarios does not fully resolve the puzzle. TON 618 represents a growth rate so extreme that it challenges the upper limits of what current models predict. Many astrophysicists suspect that objects like this are rare outliers, the cosmic equivalent of trees that find the richest soil in the earliest forests. Others believe that the early universe was more capable of producing massive seeds than we once imagined, hinting at physics that may be missing from existing theories. What is certain is that TON 618 could not have grown this large by ordinary means. It reflects a period of cosmic history when black holes had access to conditions we can no longer observe. Today, vast reservoirs of untouched hydrogen, dense environments shaped by rapid galaxy formation, and a pace of evolution far faster than anything in the modern universe. The enormity of TON 618 is not just a measurement, it is a clue that the early cosmos was a place where giants could form in ways that remain hidden from us, waiting to be decoded through light that began its journey more than 10 billion years ago. To understand how TON 618 became a cosmic giant, we have to step back into the universe as it existed more than 10 billion years ago, a universe profoundly different from the one we see today. Galaxies were smaller, denser, and more chaotic. Gas clouds crashed together with far greater frequency, forming new stars at astonishing rates. The cosmic web itself was still tightening, drawing matter into young structures that glowed with the energy of formation. This environment was fertile ground for black holes, giant reservoirs of pristine hydrogen untouched by generations of stars filled the early universe. Because this gas lacked heavy elements, it could collapse more efficiently, feeding young galaxies and their central black holes with remarkable speed. Streams of cold gas funneled along the cosmic web poured into the centers of forming galaxies, creating the perfect conditions for rapid accretion. Galaxy mergers were far more common in this era, and each collision drove even more gas toward galactic centers. With every merger came gravitational disturbances that stirred the accretion disks and compacted material into dense flows. These inflows could sustain black holes at high growth rates for millions of years. In such a setting, a supermassive black hole could double its mass again and again, climbing toward the extreme scales observed in objects like TON 618. The radiation environment was also different. The universe was still transitioning out of the so-called cosmic dawn, when the earlier stars and quasars were ionizing the intergalactic medium. The light from these early giants carved out enormous bubbles of energized gas, changing how matter cooled and flowed. Within these regions, black holes could grow rapidly without the stabilizing influences present in mature galaxies today. Yet even in this energetic young cosmos, TON 618 stands out. Its luminosity indicates that its black hole was consuming material at one of the fastest sustainable rates known to physics. The gas around it was hot, dense, and turbulent, yet somehow stable enough to maintain a blazing accretion disk that endured for millions of years. This level of sustained activity suggests that TON 618's host galaxy was unusually rich in fuel, perhaps forming in a region where matter accumulated more quickly than average, and the light we see today, stretched and reddened by billions of years of cosmic expansion, still carries the imprint of that era. It shows us a time when the universe was younger, hotter, and more dynamic, a time when the seeds of the largest black holes were planted. TON 618 is not merely a relic of that period. It is a direct messenger from it. Its brightness is a record of processes that have long since faded from the modern cosmos. In the early universe, giants like TON 618 were rare, but the conditions that allowed them to form were real. By studying this quasar, astronomers can reconstruct a period of cosmic evolution when matter flowed freely, gravity acted quickly, and the universe was capable of building structures of overwhelming scale. The brilliance of TON 618 is difficult to comprehend. This single quasar releases more energy than entire galaxies containing billions of stars. Its luminosity is so overwhelming that the light from its host galaxy is completely drowned out, erased beneath the glare of the accretion disk. If we could stand at a safe distance and look directly at the quasar, it would outshine everything around it, with a radiance that borders on the unimaginable. The source of this power lies in the furnace of the accretion disk. Gas spiraling toward the black hole compresses and heats until it glows with ultraviolet and X-ray light intense enough to ionize anything it touches. Magnetic fields snap and twist in the turbulent flow, accelerating charged particles to near-light speeds. Those particles emit radiation across the spectrum, creating a signal bright enough to reach across 10 billion light-years of expanding space. Surrounding the disk is an even more chaotic region known as the Broadline Cloud. Here, vast quantities of gas orbit the black hole at tens of thousands of kilometers per second, illuminated from within by the quasar's ferocious glow. Every atom in this region is bombarded by extreme radiation, producing emission lines so broad and energetic that they reveal the violent speeds of the orbiting gas. It is this chaotic halo that tells astronomers just how massive the central black hole must be, but TON 618's power does not stop at light alone. The quasar drives enormous outflows, quasar winds capable of sweeping across its host galaxy. These winds move at tremendous velocities, pushing gas outward and stripping entire regions of their star-forming material. If the flow becomes strong enough, it can quench star formation altogether, leaving a galaxy that glows only with the memory of its past. In this way, TON 618 is not just a passive monster. It is an active shaping force capable of altering the evolution of its entire galaxy. The scale of this radiance is staggering. At its peak efficiency, TON 618 emits energy equivalent to trillions of suns. Even at a distance of billions of light-years, the quasar remains bright enough to be seen in ground-based surveys. The fact that its light has survived such an immense journey, stretched red-shifted and dimmed by cosmic expansion, speaks to how powerful the source must be. If TON 618 were placed in the Milky Way, its glare would overwhelm the night sky. The accretion disk alone would be far brighter than the full moon, visible even during the day. Space near the black hole would blaze with radiation so intense that no planet could survive within thousands of light years. This comparison helps reveal the true scale of the quasar, a cosmic lighthouse so powerful that it reshapes its surroundings and announces its presence across a significant fraction of the observable universe. Yet for all its brightness, TON 618 represents only the visible surface of a far greater mystery. Its light tells us what the accretion disk is doing now, or rather what it was doing 10 billion years ago, but it does not reveal how such a massive black hole came to be. To answer that, astronomers must explore the extremes of black hole theory itself, and compare this titan with the other giants of the cosmos. Among all the quasars discovered across the sky, TON 618 occupies a category that seems almost unnatural. Most supermassive black holes, even the luminous ones in the early universe, fall within ranges that models can explain. They grow from stellar mass seeds, merge with neighbours, feed on gas, and gradually climb into the billion solar mass class. But TON 618 is different. Its 66 billion solar masses place it at the extreme edge of known black hole growth, a point where familiar mechanisms begin to strain under their own assumptions. This raises a critical question: is TON 618 simply the most spectacular example of a rare growth pathway, or does it represent something fundamentally unusual about the early universe? One possibility is that TON 618 is a statistical outlier, the cosmic equivalent of a tree that happens to grow taller than all the others because it landed in the richest soil. In this view, the quasar may have formed in a region where matter was unusually concentrated, where gas flowed into the central galaxy at exceptional rates, and where early mergers occurred more frequently than average. If so, Ton 618 may not break the rules. It may simply sit at the extreme end of what the rules allow. Another idea is that Ton 618 hints at an entire, largely hidden population of giants. Surveys of the distant universe have limitations. Only the brightest objects can be seen, and even then only in certain wavelengths. If other black holes reach similar sizes but lacked the precise conditions to ignite as hyperluminous quasars, they might remain invisible to us. Ton 618 could be the blazing tip of a much larger iceberg, the only one bright enough for our telescopes to detect. More radical hypotheses suggest that the early universe could produce black hole seeds far larger than those formed by collapsing stars. These direct collapse seeds, potentially hundreds of thousands of solar masses at birth, might have allowed a small number of black holes to leapfrog the slow, steady growth of their peers. If Ton 618 emerged from such a seed and experienced continuous feeding for hundreds of millions of years, its extraordinary mass becomes easier to explain. But this scenario requires conditions that must align perfectly, extremely rare but not impossible. Some theorists even consider whether the physics of accretion in the early universe differed from what we observe locally. Under certain extreme circumstances, radiation pressure might not limit accretion, in the same way allowing black holes to grow at super Eddington rates for extended periods. If Ton 618 spent a significant fraction of its life in this state, it could have gained mass far more quickly than models predict. Yet regardless of the pathway, Ton 618 remains an exceptional object. It pushes the boundaries of what is known, revealing the limits of current models and exposing gaps in our understanding of black hole growth. Whether it is a statistical rarity, the survivor of an extraordinary formation event, or a signpost pointing toward missing physics, one fact is unmistakable. Ton 618 stretches the imagination as much as it challenges theory. And to fully appreciate just how extraordinary this quasar is, it helps to compare it with other giant supermassive black holes that represent the upper extremes of cosmic evolution. Ton 618 is often described as one of the largest black holes ever discovered, but its true significance becomes clearer when it's placed alongside the other giants of the cosmos. Across the observable universe, only a handful of black holes approach the same scale. Each one represents an extreme path of cosmic evolution, and yet Ton 618 rises above them in both mass and radiance. The black hole at the center of M87, already a titan in its own right, weighs about 6.5 billion solar masses. When the Event Horizon Telescope captured its shadow in 2019, the world was stunned by its size and power. Yet compared to Ton 618, M87 is modest. The quasar's central mass is roughly 10 times greater, an order of magnitude leap that sets it apart from even the most famous supermassive black holes in the local universe. Another extreme object is SC50014+81A, a quasar whose black hole is estimated to be around 40 billion solar masses. It is among the few that challenge the upper limits of black hole growth. But even it falls short of the mass attributed to Ton 618. The difference is not small. It marks a significant jump in gravitational strength accretion history and scale of influence. OJ287, known for its binary black hole system and powerful flares, hosts a black hole of roughly 18 billion solar masses. Impressive, but again far below the mass of Ton 618. Its dramatic outbursts and repeating patterns make it a fascinating object for other reasons, but in terms of raw scale, it does not approach the colossal dimensions of the quasar giant. What makes Ton 618 even more exceptional is that it is not merely massive, it is still visible as a blazing quasar. Many ultramassive black holes in the modern universe have long since become quiet, starved of fuel, and hidden behind dust or low accretion rates. Ton 618, by contrast, existed in a time when the cosmos was rich with gas, allowing it to feed with unmatched ferocity. The early universe provided conditions that enabled giants like this to shine at their brightest. giving us a rare opportunity to study a black hole operating near the limits of luminosity. In terms of absolute mass, only a few theoretical black holes inferred from indirect observations or gravitational effects might exceed Ton 618. But none offer the clear hyperluminous signature that makes this quasar so easy to study. Ton 618 is not just large, it is accessible in a way other giants are not. Its light carries detailed information about its accretion disk broadline region and the extreme environment around it. By comparing Ton 618 to other massive black holes, a pattern emerges. While many giants exist, none combine mass, brightness, and distance in the same extraordinary way. It stands at a point where astrophysics meet something close to myth, a gravitational titan shining from a universe that was still learning how to form galaxies. And yet, despite its overwhelming scale, Ton 618 continues to reveal subtle lessons about how black holes evolve, feed, and influence their surroundings. Those lessons lead directly into one of the most important questions in cosmology. What does a quasar this extreme tell us about the history and fate of black holes across cosmic time? Ton 618 is more than a spectacular outlier. It is a crucial data point in the story of how black holes grow, evolve, and shape the universe around them. Because it formed so early and reached such extraordinary mass, it acts like a marker, a signpost pointing toward processes that must have operated with remarkable efficiency during the universe's youth. By studying Ton 618, astronomers gain insight into the upper limits of black hole growth and the conditions that allow extreme giants to emerge. One of the clearest lessons is that the early universe was far more dynamic than the modern cosmos. It was a place where black hole seeds could form quickly, where gas inflows were abundant, and where mergers between young galaxies occurred frequently. Ton 618 demonstrates that under these early conditions, supermassive black holes could grow at rates far beyond what we observe today. It shows that the rules governing black hole evolution are not fixed across cosmic time. They depend heavily on environment, gas supply, and the structure of the surrounding galaxy. Another important insight comes from the quasar's luminosity. Ton 618 is powered by an accretion disk radiating near the maximum sustainable rate allowed by physics. This tells astronomers that black holes, when fed properly, can convert gravitational energy into radiation with extraordinary efficiency. The quasar illustrates the full potential of accretion, a process capable of dominating entire galaxies and influencing the intergalactic medium with winds, radiation, and shocks. The black hole's enormous mass also provides constraints on theoretical models. If Ton 618 grew from a stellar mass seed, there is not enough time for it to reach its current size without prolonged periods of extreme accretion. This forces revisions to growth models, or it suggests that some seeds were born far larger than previously assumed. Such seeds could arise from direct collapse from massive star clusters, or even from exotic early processes that remain poorly understood. Ton 618 also highlights a curious tension. While the early universe seems capable of forming giants like this, quasar-similar objects are remarkably rare today. This tells us that black hole growth slows dramatically over time. As galaxies mature, their gas supply dwindles, accretion becomes less efficient, and the energetic environments that once built giants fade away. Ton 618 therefore represents a snapshot of a phase in cosmic history that is now over, a phase when black holes were racing to grow while the universe was still young. Finally, the quasar's extreme nature serves as a laboratory for testing the limits of general relativity and accretion physics. Its immense mass affects how light travels through its gravitational field, offering potential probe of space-time geometry at the highest scales. Although we cannot resolve its shadow like we can with nearby black holes, the spectral features of Ton 618 still reveal the behavior of matter in gravitational conditions that push close to theoretical limits. Ton 618 is not simply a monster lurking in the distant cosmos. It is a record of what the universe once allowed, a demonstration of processes that shape the early stages of cosmic structure. It stands at the frontier of what black holes can become, and studying it deepens our understanding of how the universe transforms simple clouds of gas into the most massive objects ever observed. The light from TON 618 began its journey when the universe was still in its early chapters, a time when galaxies were compact, collisions were common, and the cosmic web was pulling matter into newly formed structures. That light travelled across 10 billion years of expansion, slipping through intergalactic space, passing clusters of galaxies, and crossing the changing fabric of the cosmos. By the time it reached Earth, entire epochs had come and gone, stars had lived and died, galaxies had grown into spirals and ellipticals. The universe had aged into something calmer, wider and colder than the one that first shined upon this quasar, and yet the signal still carries the imprint of a powerful engine that once dominated its corner of the young cosmos. In that faint red-shifted glow is the story of a black hole growing faster than models once thought possible. It is the story of a galaxy feeding its central giant with rivers of primordial gas. It is the story of gravity pushing matter to its limits, transforming mass into light with unmatched efficiency. TON 618 is long gone from the state we observe, perhaps dimmer, now perhaps changed, perhaps even larger, but the radiation we receive preserves a moment frozen in cosmic time. Seen from afar, the quasar is a reminder that the early universe was bolder and more dynamic than the one we inhabit today. It was a place where giants could form quickly, drawing strength from the abundant gas that filled young galaxies. It was a time when black holes grew at astonishing rates, shaping the evolution of their surroundings with winds, light and energy. TON 618 stands among the most extreme examples, a beacon that reveals how mighty these early engines could become. Even though we cannot resolve its shadow or watch its accretion disks swirl in real time, we can still read the messages encoded in its spectrum. Each photon is a relic, a traveller from an era when cosmic structures were still taking shape. By studying that light, astronomers uncover not only the nature of this extraordinary quasar, but also the conditions that governed the universe billions of years ago. In this way, TON 618 becomes more than a distant object. It becomes a bridge, a connection between the cosmos we see today and the one that existed when black holes were first learning how to grow. As we gaze into that distant point of brilliance, we're looking into a past where the young universe forged one of its greatest titans. What we see is not merely a quasar, but the echo of an era, the glow of a black hole that rose faster, shined brighter, and grew larger than almost any other known to science. And in its ancient light across a gulf of time and distance, we glimpse the extraordinary forces that shaped the early cosmos and set the stage for everything that followed.